1736 Leonhard Euler Mechanics Systematically presented. The year 1736 witnessed publication of a seminal work in the history of physics, one that laid groundwork for mechanical understanding. Leonhard Euler's Mechanics Systematically presented. This essay proposes to undertake a rigorous, section-by-section examination of Euler's treatise. The goal is to systematically dissect the core claims, the arguments proffered, and the methodology that underpins his systematic presentation. It will evaluate the internal consistency and the potential influence of Euler's work, primarily focusing on the ideas, concepts, and framework contained within its pages. The aim is to reveal the subtle nuances, the profound insights, and, where they exist, the limitations of Euler's approach. This work will attempt to go beyond a simple summary, instead offering a critical appraisal of Euler's intellectual contribution. Section 1 Introduction, the foundation of mechanical analysis. Euler, in the introductory sections, established the very foundations upon which his mechanical investigations would be built. He began by defining the fundamental concepts of mechanics, which are space, time, matter, and force. He set a direct tone, making definitions precise and free from ambiguity. Space, Euler posited, is an absolute and Euclidean, providing the fixed framework for motion. Time, according to Euler, flows uniformly, a constant independent dimension. Matter, in Euler's view, is composed of indivisible particles subject to the laws of motion. Force, the agent of change, must be addressed, as its influence upon these particles defines mechanical interactions. The introduction serves as a declaration of his intentions. It clearly elucidates the principles and assumptions that would govern the entire presentation of mechanics. Euler's choice of Euclidean geometry for the context of space deserves discussion. This choice was not merely convenient, it also allowed him to build upon the geometric tradition that predated him. The work's clarity emanates from Euler's precise definitions, setting up a coherent system. Section 2 Kinematics, the geometry of motion. The second section, addressing kinematics, constitutes an important part of the work. Kinematics, as defined by Euler, deals with motion without reference to forces that cause it. This involved study of concepts, such as velocity, acceleration, and their relationships. Euler's approach involved using infinitesimal calculus, which, at the time, was a relatively innovative methodology for studying mechanics. He used the notion that a particle's position at a specific time is determined by its coordinates. Euler then advanced to the idea that the particle's velocity is the rate with which a change in position is occurring, which can be written as the derivative of the position with respect to time. Acceleration, as the rate of change of velocity, would have a similar mathematical description. The use of calculus in describing motion, as Euler presented it, was not only a mathematical convenience, it was a transformation in how one could understand motion itself. This section sets up the framework for future discussions on dynamics. He emphasized the vectorial nature of quantities, such as velocity and acceleration. Euler showed that these quantities have both magnitude and direction. This focus on direction in addition to the magnitude would later prove crucial for understanding complex motion. Section 3 Dynamics, the laws of motion. Dynamics occupies the core of Euler's system. Here he articulated the principles that governed motion. Beginning with Newton's 3 laws, Euler gave, in clear detail, the law of inertia, that a body continues in its state of rest or motion in a straight line unless affected by a force. He then stated the law of acceleration, establishing the relationship between force, mass, and acceleration. He also proposed the law of action and reaction. The core of Euler's contribution lies in his mathematical expression of the laws. Euler used differential equations to analyze the motion of particles under the influence of forces. Consider a simple case where a particle is subject to a constant force. Using Newton's second law, Euler shows how to determine the particle acceleration, velocity, and position over time. Euler also extended his analysis to encompass various types of forces, including gravitational forces and elastic forces, detailing the motion for each force type. He did not only state the laws, he also exemplified how to use them to solve specific mechanical problems. He solved problems of projectile motion, of a body falling under gravity, and the motion of a simple pendulum. Euler illustrated how to obtain solutions by careful formulation of the equations of motion combined with the use of calculus. The systematic use of differential equations was a decisive step in establishing mechanics as a branch of rigorous, quantitative science. Section 4 Central Forces and Conservation Laws. Euler continued to address the specific case of central forces, where the forces act along the line joining the two bodies. Here, Euler turned into consideration of the conservation of energy and momentum. He showed that, for a particle moving under a central force, the product of the distance from the center of force and the particle's velocity, perpendicular to that direction, is constant, which represents the first integral of the motion. He then proceeded to the concept of energy conservation. If the force is dependent solely on distance, then total energy remains unchanged. This section's mathematical detail highlights Euler's contribution to the understanding of conservation laws. He not only stated the laws, he also showed how they could be used to simplify the analysis of mechanical systems. This methodical demonstration was influential in the acceptance and widespread use of these conservation principles. Section 5 Motion of a rigid body. Euler advanced, further expanding his investigations to encompass the motion of a rigid body. This extension required the introduction of new concepts involving rotational motion, moments of inertia, and the center of mass, where Euler extended the ideas and methods introduced for a single particle to incorporate the motion of an assemblage of particles. Euler defined the center of mass and showed how to calculate its motion, thus reducing the complicated motion of a system of particles to the motion of a single point. Next, Euler introduced the concept of moment of inertia, which measures the resistance of a body to changes in its rotational motion. The introduction of moments of inertia was crucial for establishing quantitative descriptions of rotations. He then explored the motion of a rigid body about an axis, considering the effect of external forces, torques, and the calculation of angular acceleration. Here, again, Euler applies the same techniques to solve more complex problems. He investigated the motion of a rigid body under the influence of gravity. Euler's analysis served as a foundational contribution to the field of rotational dynamics. Section 6 Problems in Mechanics Applications of the Principles. Euler devoted space to illustrating, with different examples, the application of the principles he laid out. These problems covered a wide range of mechanical systems, from simple pendulums to more complex systems, such as the motion of a projectile and planetary orbits. These examples were not only demonstrations of his understanding, they were also intended to serve as a teaching tool. Each problem was presented in a step-by-step manner, beginning with the equations of motion, followed by solution strategies, and finally, the solutions themselves. The problems served to illustrate the power and universality of the mechanical principles that Euler had developed. The selection of problems that Euler chose shows a careful consideration of the various types of mechanical situations. He included problems that showcased the application of conservation laws, the use of calculus, and the importance of choosing appropriate coordinate systems. Euler's work helped solidify the theoretical foundations, while also demonstrating the relevance of classical mechanics to the world. Section 7 The importance of Euler's work, legacy and influence. Euler's mechanics systematically presented, beyond its technical contributions, has had a lasting impact. Its impact lies in its systematic organization, its precision, and its emphasis on mathematical rigor. Euler's work became, quickly, a benchmark for the presentation of mechanics. He not only developed the theoretical foundations but also established a way that they should be taught and applied. His work provided the model for works which then followed for many generations. The emphasis on mathematical rigor was an important characteristic of Euler's work. The introduction of calculus as a primary tool and the use of differential equations elevated the precision of the analysis. Euler's work allowed for the formulation of complex problems that could not be solved using only geometrical methods. He also had a great pedagogical influence. The clarity of the presentation and the step-by-step solutions made his work accessible to many with an interest in mechanical analysis. Although Euler's work was not without its limitations, representing a snapshot of what was known at the time, its influence on the development of mechanics is unquestionable. Euler, through his efforts, provided a foundation upon which generations of scientists build. Conclusion: Euler's mechanics systematically presented remains a landmark achievement in the study of mechanics. Its deep insight, systematic organization, and rigorous mathematical treatment would shape the path of physical science. This work, in considering Euler's own claims, has shown the meticulous manner in which he approached the study of motion and forces, his rigorous use of calculus, his clear articulation of the laws of motion, and his investigation of the application of these laws to diverse mechanical problems contributed to the establishment of mechanics as a quantitative science. The work is not without its limitations, reflecting the knowledge of the era, but its profound influence on the framework of physics studies is unmistakable. The work's lasting influence stems from Euler's approach to presenting mechanical principles. The focus on clarity, the systematic approach, and the emphasis on mathematical rigor became, then, a model for future scientific endeavors. It stands as a testament to the power of mathematical reasoning, providing a foundation still influencing how we perceive motion and the forces that govern the universe.